Hi, my name is Sheridan. I am the circuitry artist, and I have not been on for a while, so I wanted to show you why I have not been on for a while. So I'm going to run through some of my projects here. This is the butterfly amp. It's still attached. Sorry. Cell phone camera angles, one-hand operation. Sucks. Really sucks. Anyways, let me... God damn it. Everything's attached, so I'll just try to, angle the camera. So, I've got myself a few things. I borrowed this benchtop power supply from work. I built this little device, which is just basically a 2030A that's running a virtual ground. I've got this block here. What is it called? A terminal block. And right here, I have what was the prototype of my op amp. Unfortunately, it does not work. All it does is just make the emitter resistor really, really hot. And I think that's because it's trying to turn on both transistors at the same time. So, the idea, and I think the reason for that was because in Falstad, the only way that I was testing my op amp was to drive it to its absolute limits. However, when I put a feedback loop on it, it tends to really drain current. Like really, really, really drain current because it's not being too driven to one limit or the other. Even when you have no output, load output, it sucks up current, and it's... So I'm going to redesign my op amp so that with this I have these transistors here. These transistors are a current mirror, and I figured out a way to take out this current mirror. So there's only one current mirror that's sucking current through both of my input transistors. And then I have these, which essentially... So the current mirror will pretty much suck current through the input transistors. And so when one of them is turned on, when the right one is turned on, it'll suck current out of these pre-outputs at the very end there, before they go to the final output stage. So I'm going to redesign it so that instead of sucking current, it pushes current in, and that way we don't have to have... Sorry, these camera angles. Still getting used to this. We don't have to have these transistors on the end to have current sucked into them so they can feed these end output transistors. So, that is the butterfly amp project. The other exciting project that I want to get to is this thing right here. Is a slick little board that I built for bridge amplification using a tiny little op amp. Now, the problem with it was I had it all built, I plugged it all in, and it sounded terrible. Just absolutely terrible. And the reason for that is because when you have a complementary transistor pair, you sort of have a dead zone in the middle of about 0.6 volts, and if you use a Darlington pair, you have double your dead zone. So you have 2.4 volts, where if any part of the wave falls within that 2.4 volts, nothing happens on the output. So what I did is I put the emitter-base junctions into the feedback loop, and what that does is it makes the output of the op amp jump over the dead zone because you have infinite resistance in the dead zone. And when you have infinite resistance on an op amp, you have a gain of infinity. So essentially, if anything falls in that dead zone, its gain will be infinity, and as soon as it goes outside the dead zone, the gain will be whatever the resistance is that's left over after the base emitter junction chain. Hopefully, I can explain that better in future videos, when I have visuals and current flow and whatnot. So, the problem that I was running into with these was that the slew rate on my op amp was, I think, 1.7 volts, and I have a jump, or 1.7 volts per microsecond, and so I have a jump of 2.4 volts, which means it was taking approximately, let's see, 1.47, I haven't done the math on it, but that would have been about 2 microseconds to make that jump, which means there are little notches in the wave that are causing a whiny, buzzy, hummy sound whenever you have audio on it. So, I went to Mauser and I got op amps that can do 13 volts per microsecond. And hopefully, we will not be able to hear the process of jumping over the dead zone. Let me see if I can show you what that does on the wave here. Let me pause the video and set up the circuit. Okay, so let's see if I can tolerate the camera angles on this because I'm working with the cell phone camera. So, here's what I got set up. This is the inside of a LM741, which is similar to what I'm using, but not exactly, but it's similar. So, here is our output wave of the op amp, and as you can see, there's these sharp jumps that it's doing to sort of accelerate the wave over the dead zone of the op amp transistor, or sorry, the output transistors that are right here in Darlington pair. So I have the base emitter junctions go all the way through to the feedback loop back to the negative input. So they're part of the feedback loop. Now, because these jumps are sloped like that, those slopes cause little notches. Those slopes are entirely in the dead zone. So it will leave me with these notches in my waveform on the output output resistor, or actually our load resistor. So watch what happens when I remove this little capacitor. Here, let me make sure I've got the right hotkey on. I'm going to remove this little capacitor, which will make our waveform, bam, instantaneous. And so we can see that the more speed there is on our dead zone jump, the cleaner our wave is. Here, let's remove the gonna remove the current view. Okay. So yeah, it's a nearly perfect wave. You can't even see any distortion on it in the scope. If you were to put it on a frequency analyzer, you would not see any harmonics whatsoever. So, I don't know why they even have that capacitor there. It's stupid. So this is why I'm working so hard on designing my own op amp that can handle symmetrical outputs. So that's all I had for today. I will catch you next time.